Hello, everybody. My name is Dayong Wang. I'm applications engineer for RF power devices. Today, I'm going to introduce the 65 volts LDMOS technology from NXP, which is MRFX-Series. I'll give a little bit background on the RF power product lines and existing 50 volts rugged series. And then I will go into more detail on the MRFX series with some application circuit. And I'll also talk about device packaging and the thermal resistant impact on the reliability. So here is the structure of the RF power product line for NXP. So we have the main unit is the cellular, and we are top supplier for this market for the RF power devices. And then everything else uses RF power, solid state RF power devices will fall into industrial. It includes ISM broadcast and LAN mobile, which is a low power and low voltage. And then aerospace and defense, this is mainly a post application. And also we have solid state cooking. So this device I'm going to introduce is under this market, is ISM. So these are existing 50 volts devices. We call it rugged series. The rugged means these devices can withstand 65 to 1 load VSWR at full rated power. Started 2009, we first introduced 300 watts device, and then each year we developed different power level to like 600 watts, 1250 watts, and then we also develop some lower power for driver. And then start from 2013, we decided to put this same die into the plastic package for the cost saving. So last year, we released the highest power. Last year, it was 1500 watts. So as the power goes higher and higher, we have to do something differently. That's why we came up with this MRFX series. It is a 65 volts LDMOS and was designed for easy of use. There are some several advantages for this series. First, it has higher output power that enabling fewer transistors to combine, and higher output impedance, so making it easier to match to 50 ohm. With the higher voltage, it will drop the system current that's enabling lower losses. So it has higher breakdown voltage, which is 182 volts, and that's improved the ruggedness and also allowing for higher efficiency classes of operation. So similar impedance in the higher power makes this transistor pin compatible with the previous 50 volts generation. So you can use same PCB design. And this series also helps simplify the matching. And here is why. So this simplified output impedance equation. As the output power increases, your output impedance drops. So one way to keep the output impedance reasonable or manageable level when the power increases is to also raise the operation voltage. For example, 1800 watts push-pull transistor, the impedance at low frequency will be at 50 volts. It's about 1.8 ohms. And the transformation ratio to 50 ohm is almost 28 times. On the other hand, at 65 volts, the output impedance will be 3.4 ohms. It's almost double the output impedance at the 50 volts. And the transformation ratio to 50 ohm will decrease to 15 times. This will make your matching much easier. At high frequencies, the output capacitance matters. So when you increase the voltage, that also makes LDMOS chip size smaller. That will lower the output capacitance. So this is the first device we released under this MRFX-Series. It's MRFX-1K80H. It is 1800 watts CW capable, and it works from 1.8 to 470 megahertz. And it can operate as 65 volts. So the minimum breakdown voltage is 182 volts. And also it's also rugged devices, can handle 65 to 1 VSWR. And it's pin compatible with 50 volt series, which is like 1K25 and 1K50, which we released before. Here's some typical performance. We just measured this device using the previous design. And you can see there are some empty spaces. So when I wrote this presentation, we haven't finished all the evaluation. Based on this data, with the different signal or either pulse or CW, the power will be start from 1500 watts to 1800 watts. The efficiency is from 65% to 70%. NXP has the full lineup solutions. For example, this is you can use a Mimic pre-drive, and then the mid-power driver to drive 2 amp of this 1800 watts device. So this MRFX series is really focused on scalability. That means when you drop in the 65 volts device into the existing design with the minimum tuning, and if you increase your operating voltage, you can get higher power. Or if you keep the existing operating voltage like 50 volts, then you get better reliability. This is an application circuit designed for 1.5T MRI system. It's a 3 by 5.5 inches and at 65 megahertz with 100 microsecond and 10% pulse. The P1 dB is about 1600 watts, and P3 is more than 2 kilowatts at 65% of efficiency. So this is another circuit also developed for MRI system. It's 5 by 5 inches and works at 128 megahertz. So the P1 dB is about 3.2 kilowatts, and P3 is higher than 4 kilowatts. So also the efficiency is about 65%. So as the power goes higher, and with the several hundred watts of power dissipation, so the device package design is critical. And we already have the 2 different types of packages. One is we call IR cavity ceramic. The other one is traditional plastic over-molded. They both have pros and cons. Like for the ceramic, it uses high conductivity metallic die attach, but the flange material has less thermal conductivity compared to over-molded. It uses pure copper, but that one uses soft solder die attach. That also makes thermal resistance higher. So now we came up a new design So it uses this copper heatsink, and from here we use high conductivity metallic die attach. The same thing, we use the overmolded process. This will make the package thermal conductivity increase significantly. So how this thermal resistance impact on reliability? This is an example from previous transistor, which is a MRF-1K50. If put this device in the new plastic package, the RTH thermal resistance will drop from 0.1 to 0.068. That's more than 30% of drop. Let's assume that with the 100 degrees C case temperature, and the output power is 1400 watts CW with 78% of efficiency. So there will be a total of 1800 watts of power goes into the device, and you will have 400 watts of power dissipated to the heatsink through the package. So the junction temperature with in the plastic package, it will be 127 degrees C. In the ceramic package, the junction temperature will be 140 degrees C. And how these temperature numbers translate to the reliability? For the 140 degrees C, the MTT-F is 6 million hours. For the 127 degrees C, the MTT-F will increase to 11 million hours. That's almost double. So the rule of thumb, each 10 to 15 degrees C increase in junction temperature will cut your MTT-F in half. So this is a MRFX-Series, higher power, no compromise. For more information, please visit www.nxp.com/rfpower. Thank you for your attention.